Today let's take a look at energy exchange with a circuit element, and that leads us to the concept of electrical power, as we'll see. So we're looking at energy exchange and a circuit element, but I want to look at it from a very general perspective, in that I'm going to have a steady current I going through an arbitrary part of a circuit. And between A and B, which I can put right up here at the end, I'm going to put really anything, which I'm going to call a black box. I don't even have to know what's in there, especially, although you usually do, but it could be anything. It could be a television set, it could be a radio, it could be New York City, yeah. It could be the Hoover Dam electrical power generation plant, so really anything. All I just have to have is I have to be able to measure current that is going through this circuit. Goes through here from A to B. Current I enters at A and leaves at B. And also, I need to be able to measure the potential at A and the potential at B in front and behind. And so let's look at that. And I want to focus first on the charge that moves through. I know that in time delta t, an amount of charge delta q moves in and a delta q moves out. So in effect, I've got a delta q that goes from A to B. And if I know the current, I assume I've measured that, and I know the time delta t, then I can get that amount of charge. It's just I times delta t. And now then, let's calculate the charge's change in energy as it moves from A to B. Its energy at A is its kinetic energy plus its potential energy. And at B, it's just whatever the kinetic energy is and the potential energy at B. And I'm assuming we've got a steady current here, or it could be instantaneous current, but I'll assume that it's a constant steady current like we have been throughout all of this. And if that's the case, I know that the kinetic energy of the charge that's moving through in this current, the kinetic energy at A and the kinetic energy at B is the same. And the reason I know that is because the current density is the current divided by the cross-sectional area. I assume it's the same area wire going in and out. And that's equal to N sub F Q sub F times the drift velocity. But if I've got a steady current, constant K, or constant I, then the velocity is constant. And if the velocity is constant, then kinetic energy is 1 half mv squared. And so the kinetic energy is constant through there as well. So the same kinetic energy enters and leaves. Potential energy, on the other hand, can change depending on what our measurements for the potential at A and the potential at B are. But just remember, potential energy is just the charge times the potential. So when delta Q is over here at A, its potential energy is delta Q times the potential at A. And likewise, the potential energy at B is just the charge, delta Q, that's there when it's at the point B up here. So it's the potential at that point. Well, let's look at the change in energy of the charge. And the change in energy is just the final minus the initial. Its final was up here, current's going this way, is the energy at B, and the initial was the energy at A. So the change in energy is EB minus EA, but we've got those two expressions up here. KE plus delta Q VB minus KE plus delta Q VA. But as I've argued, the kinetic energy is the same, so those terms cancel. And I get that the energy that's gained by the charge, delta E, or the energy delta E that's gained by the charge delta Q, is given by delta Q times the difference in potential from B to A. Or from A to B, I should say. But, again, we know that delta Q is I delta T. Here. And so I just plug in for the delta Q here, I delta T. And that gives me delta E is I delta T VB minus VA. And then usually one doesn't look at the energy per se, but the energy delivered in time delta t. And that's the power. And power I usually represent by script p, just so that I don't get it confused with momentum. So the power p prime. Prime in this case is the power that is the energy per time that the charge is gaining. So the delta Q is gaining. And power is just the energy used in the time it's used in, or the energy gained in this case by the charge divided by the time it was gained in. But the energy gained by the charge is up here, and the delta T is just the delta T, and so those cancel. And we get the expression that the power gained by the charge delta Q. It's the rate at which energy is being supplied to that charge is just I delta V. And I've written that out in some detail there. Power supplied to delta Q by really whatever's inside that box. Delta V could be positive, negative, or zero, depending on if the charge goes from a low to a high potential, or a high to a low potential, or if there's no potential difference at all. And that's okay insofar as we go here, but we're usually interested in the power that whatever that device is gains or loses. So we're usually, if it's a battery, we want to know how much power that battery is supplying. If it's something that's using the power, we'd like that to be the device that's in there. How much is it used? But by conservation of energy, whatever energy is lost by the charge has to be gained by the black box. And so whatever's in the black box will get this amount of energy, delta E, which has to be the negative of whatever was gained or lost by the charge. So another way to say this is the power gained by the black box is equal to minus the power gained by the charge. And since we have P prime as I delta V, then that gives us P equal minus I delta V for the power that is supplied to whatever's in that black box by the current. Now, lots of books simply write this relationship up here as the power is equal to I times V, with the idea that, well, you're plenty smart enough, you can go through and decide whether whatever you've got in that black box is using power or it's generating power, giving power to the rest of the circuit. So you just put the magnitudes of the potential difference, that's the V in this one, and the current going through it, and then you decide whether you're using it or giving it up to the rest of the circuit. For a pure resistor, we have the following. Let's suppose what's in the black box now is just a resistor, and I've got a current I going through here. Remember, resistors, I can mark the polarity. Current flows, if it's flowing in this direction, always flows from high to low potential, so I'll mark the high and low sides there. I use our formula in the very explicit form in the minus I delta V. This is the power that's going to be gained by this resistor in this case. So I get minus I. But remember, delta V is plus or minus IR, but as I move across this from A to B, I use the last sign I hit, so I use the negative sign. And these two minuses cancel, and I get I squared R. Notice, no matter what direction the current's flowing, if it's flowing from left to right or right to left, if it's going from left to right, it's I. If it's going from right to left, I guess that would be minus I. But by the time you square either I or minus I squared, it's the same number. So the resistor uses power no matter what, gains power no matter what direction the current flows through it. So you'll often see this relationship P is equal to I squared R. Since V is equal to IR, then you also see these. I can pretty obviously um, take one of the I's and the R here, and that becomes a V, and so I have I times V. Or I can solve this for I, V over R, and plug it in up here and get V squared over R squared, and one R will cancel at the top, and so I get these. So these are other uh, formula that are sometimes useful too. But one implies the other, assuming you've got the V equals IR relation. For an ideal EMF, that situation's a little bit different. Yeah? So let's look at the case where in our black box we've got just a pure circuit element, which is just an ideal EMF of voltage E, current going in this direction. Uh, Same story. The power, in this case, to the circuit element is minus I delta V. That's our general relationship. VB minus VA. Well, the potential difference is E. And again, the long bar is positive, the short bar is negative. If I go from A to B, I'm increasing the potential. So delta V is a positive E. And I get that the power delivered to the circuit element, namely this EMF, is negative. And that means that um, both I and E now are positive, and the negative sign indicates to us that the battery or the EMF is losing energy. So this is a case of discharging the battery. It's in use going into producing that current, probably. Now, if I turn that around, let's suppose that I've got current that I know is flowing in this direction, and I've got an EMF that's the opposite direction to the one above it. So I've turned it around. So now the current is flowing from positive to negative. Still the same formula, still VB minus VA, but in this case I'm going from high to the low potential side. So the magnitude is E, but it's a drop, and so it falls by minus E. And now then I get I times E. Both of these are positive. I and E are positive. And in this case, the battery is gaining energy by this amount, or energy per time really. Power is being supplied to the battery. And that's a case where we're charging the battery. The units of power are pretty easy to figure out. Just use that P equals IV expression. Current in coulombs per second. A voltage is in volts, but a volt is a joule per coulomb, and those go out, and you get a joule per second, which is a watt. Not a unit from this semester, but one you should have seen last semester for a mechanical power, which you were doing. Notice also from here power in watts, current in amperes, voltage in volts, and so 1 watt is 1 amp times a volt. More commonly, you'll see things like kilowatts, kW, 10 to the 3 watts, or megawatts, or sometimes even gigawatts, 10 to the 9th watts. Sometimes you see problems like this, in which well, let's maybe save that for the next part as an example problem, but we'll go over this on the next video. How about that?